mass. And how to find mass moment of inertia for, let's see, this is called M1, M2. Since we know if we only have a disk, we know the center mass is right at the center, right? And if we only have a bar or rod, we know mass center is, this is a G, G2, G1. But when you put them together, how to find the location for the center mass? So from, you probably can guess, let's use a different color. If this is G2, G1, and then the new mass center gonna be somewhere around here, right? Let's call this G prime. But how to find out that location, exactly location of that G prime? So if you want to find out what's the location for that G prime, first thing is to set up a reference point. I would use this disk, the center of the disk, as the kind of the origin to find the new center mass. In order to find, let's call this Rx. In order to find that, we'll use Rx equals to the first mass times the distance from the origin, which is, let's call this point O, this is a new origin, from the origin to the center mass of the first mass, R1, and plus the second mass, plus times the distance from R2 is the distance from the origin to the center mass of mass 2. And this divided by the total mass. In this problem, we can plug in. It's going to be M1 times 0, since I choose the origin at the center mass on M1, which is just the center of the disk. So there's no distance between the origin to the center mass of the disk. Plus M2, R2. R2 is the distance between the center mass of M2 to the origin. This is going to be R2. And the total mass is going to be M1 plus M2. So it's going to be M2, R2, M1 plus M2. So that's how you find the coordinates for the new center mass if you have a combined geometry. You know the center mass for each individual, and the combined center mass location can be calculated in such way. Okay, once you find out the location of the center mass, you can identify what is the new moment of inertia. Let's call this G prime. And the new moment of inertia of this combined disk and the bar, they're welded together, and can be found by using the center of the moment inertia G1, which is this disk, plus D, M1 times D. This D is the distance between the center mass of the disk to the G prime, which is this point, G prime. So let's say this is from G1 to G prime square. Remember, this is, if you just look at this, this is a parallel axis theorem. We're not done yet. Here we need to add the moment inertia of the disk, of the rod, which is G2 plus M2 times distance. What is that distance? It should be from G2 to G prime. So D G2 G prime square. Okay. So now you know, if you want to find the mass moment of inertia of a kind of irregular geometry, and you cannot have to know what is the location for center mass of that combined geometry first. You need to find out what is Rx, then you can use that information to find out what is the moment of inertia by using the moment inertia of the first mass to the new G prime plus the moment inertia of the second mass to the G prime. That makes sense. And this thing, if you work on one of your homework problems, you will run into a problem like this. You can use this to find out the moment of inertia. Okay. All right, next. This is the topic I want to mention before you're working on your homework. Next topic is we're going to look at two more examples. The first example we're going to look at it's 5B10 of your book. So on your textbook 5B10, let me check what page is that. And that's on your page 329. And so in that problem, we have a disk. And there's a rope wrapped around the disk. Let's use a different color. One end of the rope is fixed on a block. And this rope is wrapped around this disk. At the other end of the rope, there's a force, tension, like pulling force F. And the disk is resting on this slope with the angle theta. So what are the givens? We do know what is a mass. Mass equals 25 pounds for the disk. And we know kg, radius ratio is 4 inches. And we also know the pulling force, F, is 20 pounds force. We know the radius of the disk, it's 0.5 feet. And we also know the theta. Theta equals 36.87 degrees. In this problem, we want to find Okay. Determine the speed of the center G of the disk when it has rolled 8.8 feet up the incline. So we want to find what is VG. VG, let's call it VG2, since at the beginning it's rest. After 0.8 feet incline. Okay, so if you look at this problem and we know the force, we know the mass, what we're trying to find is what is the speed after a certain traveling distance. So for such problem, and it's kind of indicates you need to use work energy equation to solve such question, such problem. Okay, solution. Let's look at how we can apply work energy equation in this problem. Okay, first, should always have free body diagram and coordinate system. Let's start with free body diagram. The disk. And the disk, we have a weight force going down. It's WG. And one end of the rope, there's pulling force F. On the other end of the rope, let's call this force FB. It's also pulling the disk. Since the disk is sitting on a slope, right? And so we know the normal force has to be applied at a certain angle perpendicular to the surface. And yeah, those should be all the forces. One more thing I forgot to mention, the given is there's no slip. So this is a no slip problem. So this FB force here acting at the bottom of the disk, it's serving as a force on the rope as well as the kind of, you can treat that as a friction force at the contact surface. Since we have this slope with the angle theta, I will set up my coordinate system with this angle theta, J and I. Okay, now we have this first step down by figuring out what is the free body diagram and what is the coordinate system. Next, we can look at how can we apply work energy equation. And last Friday, we talked about the main difference between work energy equation in chapter 4 and chapter 5, right? The main difference comes from the kinetic energy. It's calculated in different ways in this chapter. And we mentioned we can pick two different points to calculate kinetic energy so that we can simplify the equation. And do you remember which 2 points we talked about last week? Let me label them on the diagram. So the center mass is going to be point G. The contact point, no slip contact point, is going to be point C. So in this problem, you can either choose G or point C to calculate kinetic energy. Either way is okay. And remember that C, the reason we can pick C is because the velocity at point C is 0. So for kinetic, to calculate kinetic energy, you can either pick the center point, the mass center, G, or you can pick any point that has velocity equal to 0 on the rigid body. In this problem, the contact point, which is the no slip point, it has 0 velocity. Therefore, you can either pick G or C. In this, let's call this approach number 1 or approach number 2. Let's start with just use approach number 1, pick center mass. Okay, use point G. Then let's look at the kinetic energy at position 1. So this disk is the force is applied when everything is at rest. So at the beginning, there's nothing is moving. Therefore, velocity is 0 and T1 is 0. And let's look at T2. T2 is kinetic energy at position 2. So the position 2 we're looking at here is after this disk is traveling 0.8 feet incline. So incline towards to the top of this slope. And at position 2, we know the disk should have some some speed. And so since we picked point G, the kinetic energy equation goes 1/2 mvg2 square plus 1/2 ig omega 2 square. Remember, that's the main difference we talked about last time. If you just look at the first term here, 1/2 mvg square, that's similar. That's exactly the same thing we did in chapter 4 for particle work energy equation. And in chapter 5, when we have rigid body work energy equation, this is the extra term you need to add when you're looking at pick G point G for kinetic energy. Okay. And since Ig, let's look at here. We know mass, we don't know Vg2. Here, the Ig is not given directly, but however, we do know the radius ratio, which is 4 inches. And that pretty much tells us what is Ig. So Ig equals m times kg square. And omega 2 here, do we know anything about omega? Omega is angular velocity, right? So angular velocity, how can we find angular velocity? So we can use something we learned in chapter 2. Let's say in chapter 2, we learned relationships between 2 points. If we're talking about velocity, Vg, point G, which is mass center, equals Vc, which is a contact point, plus omega cross product Rg/c. Remember this equation? Since Vc, it's the instant center of the disk, so Vc is 0. And therefore, this Vg equals omega is omega k cos Rg/c. It's a position vector pointing from C to G. This is point C, point G. From C to G is positive J. That is R positive J. And from here, you will end up with a relation that Vg equals K cos J is negative omega R on J direction, on I direction. From here, you can find a relation, find what is Vg. Vg is just negative omega r. Okay, so now we kind of know a little bit about what is omega 2. And this Vg2 is the unknown variable we try to solve. And so far, we found out the kinetic energy at position 1 and position 2. And we can look at what is we can plug in everything to get an expression for T2. Okay, so T2 goes 1/2 m, can replace Vg2 with this negative omega r. So negative r omega 2 square plus 1/2 mkg omega square kg square. Okay, and if you look at this, we can combine terms here. So both have m omega, and half. So we can get expression for T2. That is 1/2 times m times 1 plus kg r square vg square. From this equation to this equation, simply replaced all the omega 2 with negative Vg over r from here. And now we end up with the equation expression for T2, which is kinetic energy at position 2. And like you mentioned earlier, you can either pick point G or point C to analyze kinetic energy. In this case, if you pick point C and if we pick number 2, you pick point C and your kinetic energy equation gonna just be 1/2 Ig omega square. Oops, this is IC, sorry. And your equation may look simpler, but you will find out you're going to do the same amount of work to get at end up with the same expression here, no matter which point you pick. So either ways will work. Okay, now next we should start analyze the work done from all the forces. So work. So as we know, the work can be done from conservative forces. And if there are conservative forces, we can use V1, V2. There are potential energies from conservative forces. Or we can use the work done from a force, a constant force from 1 to 2 as well. And let's look at all the forces we have in our free body diagram. So let's first look at the weight force here. The weight force, and we can set up a datum for weight force. Say the initial position here is the V equals 0. So at V1, the potential energy is 0. At V2, and since it's inclined, it goes up the ramp, so we know there's positive potential energy. Start from 0 and end up with the mg. Oops. If we want to calculate the height difference, so if this is theta, and this is the length we traveled on the slope, let's call it d. And the height here it's going to be sine theta times d. So the new potential energy at position 2 can be mg sine theta d. Okay, that's the potential energy from weight force. Let's look at normal force. Normal force is perpendicular to the motion of the disk, therefore it does no work. 0. Now, other force we have is this FB. And let's go back to the free body diagram here. And that's something we mentioned last time. If you look at point C is the no slip point, the contact point of the disk and the surface. Since FB, its point is applied right at that point, and that point has zero velocity. So that's something we mentioned last time. The work done from that force is 0 in that case. Okay, what other forces we have besides wave force, normal force, and free body diagram, and the force FB? If we come back to our free body diagram here, we have this force F. And what's the work done by that force? I'm gonna call someone to see if you know the answer. Hey Cole, are you there? Do you know what's the work done by this force F? If we see we travel this distance d, this is d equals 0.8 feet. Anybody would know the answer? Okay, so here's actually a very tricky part of this problem. Do you remember I mentioned if you're driving your car on the highway, 70 miles per hour, the contact point between your tire and the road has 0 velocity, right? And at the center of your wheel, and the speed is traveling at 70 miles per hour. And what speed of the tire on the top of your tire is traveling at? Hey, Cole, do you remember that? What's the speed of that on the top of the tire? Anybody knows?
140.
Yeah, 140. So same here, if you can look at this disk, point C is a 0 velocity point, that's the instant center. And at point G, this point G is traveling at VG. If this point G is traveling at VG, and at this point, let's call this point A. And the velocity at point A is going to be 2 times larger than point G, if that makes sense. You can use instant center method to validate this. At point C, the speed is 2 times the speed at point G. Therefore, if our point G is traveling up the ramp for distance d, since at point A has 2 times larger speed than point G, So at point A, it's traveling 2 times longer than point G. So here, F, the work done by F equals 2 times FD. So this is a little bit hard to think, I think, but that's a very tricky part. If you have a rope wrap around the disk, always remember at the top of the disk, and the speed is larger than the other points on the disk. So it's traveling longer distance. I think a lot of you may just write F times D and didn't consider F is applied on the top of the disk, which is not right. Now we should have all the components we need. Now we can assemble the work energy equation. T2 plus V2 equals T1 plus V1 plus work 1 to 2. And T2, we can copy this T2 here. We have 1/2 mass times 1 plus kg square over r square, Vg2 square, and plus V2, that's a potential energy at position 2, which is mg sine theta times d. And on the other side of the equation, since T1, both T1 0, V1 0, and work down from 1 to 2 from that force F goes 2 times FD. Therefore, VG2 equals square root F 2 times FD minus mg sine theta d. 1/2 1 plus kg square r square m. So that's expression for the velocity of g at position 2. Since in this problem, mass is not given, mass is given in pound force. So m equals the pound force is given there divided by g. And if you plug in all the numerical values, you should end up with g2 equals around 5.97 feet per second. So now you should be able to see the difference here in this chapter when you apply work energy equation. I will highlight places that is totally different than chapter 4. One place is when you try to calculate kinetic energy. When you try to calculate kinetic energy, you can choose. No, my bad. You can either choose the center mass or it choose a point that has 0 velocity. And since when you choose different points, it can simplify the equation in different ways. If you choose point G, which is center mass, and the equation for your kinetic energy has 2 terms, it's 1/2 mv squared and 1/2 ig omega squared. And if you choose point C, which is a 0 velocity point, and your kinetic energy expression only has 1 term, which is 1/2 IC omega square. But be careful here, this moment of inertia is about point C where you picked. And here this is IG. It's a moment inertia about point G where you picked point G for kinetic energy. And since this chapter is closely related to chapter 2, like rigid body kinematics, so we use equations from kinematics and to find out relationship between velocity and omega, which is very important. That will help us to find kinetic energy, get rid of some variables. Then two more things is, if you have a force, either it's a force or friction force at the contact point when there's no slip. So no slip problem is a big uh, category in chapter 5. So if you have this no slip condition and the force at the bottom at the contact surface there do zero work, because at that contact point it's a special point which is has zero velocity. And if the force applied at a point has zero velocity, which means there's no motion and therefore no work. And the work done from on the top of the disk, F, do 2 times Fd instead of just Fd, because at the top of the disk, it's traveling 2 times faster than the center mass, the point at center mass. And once you have all the components for your work energy equation, you can assemble your work energy equation and to solve the unknowns. Right, that's about this example. Any questions? Okay. If you don't have questions, let's look at one more example. Let's look at example 5b2. So in this example, instead just having a disk with one radius, we have a disk with inner radius and the outer radius resting on this slope. That's a very bad drawing, I'm sorry about that. Okay, and if we know we're given the large radius, capital R and small r as the radius for the inner and outer radius of this cylinder. We know kg, which is radius ratio, and we know this is released from rest, and there's no slip. And we want to find what is Vg, the speed of velocity at point G, which is the center, mass center. And after it's traveling down the slope with a distance L. Okay, so it's pretty similar. This is very similar with the previous example we did. I just want to set up this problem and so that you can practice this by your own. So for kinetic, in terms of kinetic energy, you can either pick, let's call this G, and this point is C. You can either pick G or C to simplify the calculation, right? Just what we did previously. And everything released from rest, that would tell you that T1 equal to 0. And this gear radius gear ratio here, it basically means you can use that to find out what is the moment of inertia at point G. And something we need from chapter 2, rigid body kinematics, in this problem, it's pretty similar with what we did here. How we find the relationship between Vg and omega. In this example, we end up with this conclusion: Vg equals negative omega r. This is not a general conclusion, so do not just apply this for any other problems, because in this problem, the disk is rolling down the slope. So if you apply the equation Vg equals Vc plus omega cos Rg/c, you would end up with the relation between that equals Vg equals positive omega r instead of negative omega r. And other than that, it follows the same procedure as we did. Once you find out all the kinetic energies at T1 and T2, and you need to find out the work done from the weight force, from the normal force, from the friction force in this problem, and assemble the work energy equation, and we'll find out you have the Vg gonna be the unknown.